Hey, I'm going to do some calculus. I'm going to do some, the Chapter 2 topic problems here. I'm going to break these up into separate videos for each topic. And as I go through them, I'm going to really talk through all of the details as best as I can so that we can get as much of a review as possible from these problems. So Chapter 1, or Chapter 2 rather, limits and continuity. So let's see what we have here. The graph of the function f here is shown above. Which of the following statements is false? So I'm not even looking at the answers yet. Things that we need to know about limits is that things like this right here, this is coming into the same thing from both sides. So that limit at 2 does exist. The point is kind of like in the wrong place, but that doesn't matter for limits. So that is okay. The function's not continuous there because the hole and the point don't match up, but that limit does exist. This is fine. That would be a problem for finding a derivative because there's a sharp corner there, but we're not. We're just talking. Oh, maybe. No, there's no statements about derivatives. So here, this limit does not exist here because we've got to jump. So like here, it's coming into around 2, and then on this side, it's coming into, looks like right about 4. So that doesn't exist. This does, and this doesn't. So I'm guessing, before I look at the answers, that probably they're going to be trying to figure out if we know the difference here. That this limit exists because both things are coming into the right spot, even though the point's in the wrong place. But this limit does not, because the two sides are different. All right, so which of the following statements is false? Does the limit as x approach 2 exist? Yep. Does the limit as x approach 3 exist? Yep. The derivative doesn't, but whatever. How about this? No, that is false. Does the limit as x approaches 5 exist? Sure. And is the function continuous at x equals 3? It's continuous, yes, but it's not differentiable. But they're just asking, is it continuous? Yep. So there you go. All right. Let f be the function defined above. This is a piecewise function. Let's just check it out here before we go further. So for all x values except 2, you plug them in here, and then when x is 2, it's just equal to k, whatever k is, some number. So for what value of k is the function continuous? So I know it doesn't look like it, but this is really a question about limits. If you want something to be continuous, this function, you can't plug 2 in this because you get 0 over 0, right? But that is a 0 over 0 that just cancels out. So if you did plug the 2 in here, you get 2 times 2 plus 1 is 5. So when you do actually get to 2, 5 is where that hole is, and if you're going to plug the hole, you have to plug it with a 5. So in terms of continuity, this is really asking what is the limit as x approaches 2 of 2x plus 1 times x minus 2 over x minus 2, is whatever that limit is. If you want to plug the hole, that's got to be what the k value is. So it's kind of just connecting it to this last problem, kind of like if we were looking at a graph like this and we're like, okay, what do you want to make f of 2 equal to so that this function's continuous? Well, it would be whatever these are approaching. You'd have to plug the hole right there, right, and find that value. So this one missed. That's why it's not continuous there. All right, next. Let f be the function defined by this for all x. Which of the following statements is true? Okay, that's a little tricky because what does that look like? We need to have like some kind of concept of what it looks like, and we're not allowed to use our calculator. So I'm going to try to make a sketch of it. You know what the absolute value of x minus 2 looks like, so without the square root sign. It looks like the absolute value of x looks like this. If you put a minus 2 in there, that's shifting to over here. So that looks like this. And then if you square root things, that just kind of like bends them down, right? As they get bigger, you're square rooting them. So, you know, like the regular y equals square root of x function, that's one you should be familiar with. It looks like this. It's basically the top half of a sideways opening, like x squared kind of parabola, right? So, so this function is going to look like 1, 2, kind of like this. The two arms of the absolute value function just kind of get bent down like that. All right, so let's see. F is continuous, but which one of the, so we're looking for a true statement. It's continuous but not differentiable at x equals 2. Differentiable means you can find the derivative, and at x equals 2 you can't because there's a sharp corner there. So I think this looks good. F is continuous, sure, you can draw it without taking your pencil. There's no whole jump or vertical asymptote there, but there's a sharp corner. So it is continuous but not differentiable. So that's looking good. But let's just go through the other ones to make sure. Is F differentiable at x equals 2? No, there's a sharp corner there. And if you're thinking, well, why don't I just try to take the derivative? We don't actually have any special rules for taking derivatives of things with absolute value signs, so we really need to know what they look like. And that definitely has a sharp corner there. F is not continuous at x equals 2. Yes, it is. No whole jump or vertical asymptote. The limit as x approaches 2 of f of x is not 0. It is 0. As x approaches 2, it's getting closer and closer to 0 on both sides. Now, that is true. It's false, rather. I mean, it's true that it is equal to 0. X equals 2 is a vertical asymptote of the graph. No, it's not. So I think it's pretty clear that knowing what this graph looks like and being able to come up with a sketch of that was super important for doing that problem. All right. Number 4. The line y equals 5 is a horizontal asymptote to the graph of which of the following functions? Okay, this is a question about limits. In one of the sections, I think it was 2.3, we talked about limits as x approaches infinity. If you let x approach infinity, you take the limit of some function, and you get like a number here, then that's the same exact thing as x approaches infinity. If you're getting closer and closer to something, that's the same as saying it has a horizontal asymptote at that thing. So what we're looking for with these things, we're looking to check out what's the limit as x approaches infinity of each of these functions, and which one has a limit that's equal to 5. Right? So how about this? The limit as x approaches 0 of this is 5, but as x approaches infinity, the sine function, even with the 5x in there, just does its little sine function dance, like wiggling up and down between 1 and -1, and then we're dividing by something that's blowing up to infinity. So the limit of as x approaches infinity of this is equal to 0, because this is blowing up and this is trapped between 1 and -1. How about the line y equals 5x? Well, that just blows up, right? There's nothing going on there. I mean, just plug in infinity, 5 times infinity, that's infinity. So that limit as x approaches infinity is infinity. Here we have higher exponent on the bottom, x to the 1 on the top, and no x's on the bottom. So as x goes to infinity, that's going to get bigger and bigger. 1 divided by hugeness is going to go to 0. How about here? Here we've got an expression, same exponent top and bottom, so the limit as x approaches infinity is just the ratio of the coefficients. 5 over -1. That's -5. Ooh, close, but no cigar. And then here, same exponent top and bottom, so it's the ratio of the coefficients, and that is 5. So that's what we're looking for. All right. Number 5, let f be a function that's continuous on the closed interval from 2 to 4, with f of 2 equals 10 and f of 4 equals 20. Which of the following is guaranteed by the intermediate value theorem? What the heck is that? The intermediate value theorem, the IVT. Oh, let's see. Where did we find that? Was in section 2.5, I think, is where the IVT lives. I'm going to just flip through. I got a book, calculus book right here. I'm just going to check that because I don't want to tell you something that's not true. Let's see. Oh, there it is. Yes, the intermediate value. It is in section 2.5. But I'll tell you what it says. This is what you need to know. The IVT, it's super, super intuitive and obvious thing. The IVT says that if a function is continuous, doesn't have to be differentiable. Of course, we didn't know about derivatives back in chapter 2. If a function is continuous on a closed interval from a to b, then the rest of it I'm going to say with a picture. So if you got a function that's continuous, let's say this is where a is, and let's say b is over here. So if you got 2 points on that function, like what we have here, and it's continuous, then it has to cross every single y value in between here and here. So like this, whatever that is, like f of a, and then whatever this is here, f of b, if you look at all the y values in between these, that function has to hit all of them. So somewhere in between a and b, it's got to equal everything in between this y value and this y value. Because if it's continuous, you can't get from here to here without crossing all of those lines. Now, if you're allowed to have a jump, then you could do it. Or if you're allowed to have a hole or a vertical asymptote, then you could do it. But if you're continuous, continuity prohibits exactly those things. So that's what it means. So here for this particular case, I've got f of 2 is 10. So I've got 2, 10, and 4, 20. And that means we've got to get, so somewhere between 2 and 4, you're going to hit every single value between 10 and 20. So which of the following statement is guaranteed? So f of x equals 13 has at least one solution in the open interval from 2 to 4. I think that has to be true because there's 13, f of x equals 13, that's just a horizontal line at 13. So that's like saying f of x equals that. We got to cross that somewhere. So that's looking good, right? Because that's a value in between 10 and 20, and we got to hit it somewhere in between 2 and 4. Does f of 3 have to equal 15? Well, if it was a straight, it could, but that certainly doesn't have to be true. Does f have a maximum? No, it could just go straight from there to there. It's an open interval, not a closed interval, so if you're thinking about like chapter 5 stuff. Does f prime of x equal 5 have at least one solution? So let's see, what's the big deal about the slope being 5? Well, if you find the average slope, rise is 10 over run is 2. The average slope here is 5. But there's actually something coming up in chapter 5 that, if you haven't done that section yet, I think it's section 5.7 maybe, called the mean value theorem, that says if you find the average slope and a function is differentiable, like no sharp corners, then you have to, kind of like this theorem that says you have to hit everything, and you have to hit the average slope somewhere. But we haven't done that yet, and it wouldn't have to be true anyway, because the only thing they're saying about this function is that it's continuous. So it doesn't have to have that slope. So that's a no on that one. F prime of x is greater than 0 for all x. Well, in my little sketch it looks like it, but it could go like this. You could have some negative slopes here, some decreasingness, and then get up to there. Nothing to stop it from doing that. So it looks like A is our correct answer. Number 6, the function f is defined by this. That's, I don't know, it's kind of a helpful function to add to your repertoire of things that you know about, like y equals x squared and stuff. This is the top half of a circle with a radius of 5. And we got this piecewise function here, f of x, so from -5 to -3, and when you plug -3 into this, 25 minus 9 is 16, so that's at the point -3, 4. So between -5 and -3, with the equal signs, I got this. And then between -3 and 5, I've got the line x plus 7. So what does that look like? That's got a y-intercept of 7 and a slope of 1. Does it go through this point? If I plug -3 in here, -3 plus 7 is 4. So it does hit that same point. So it's like the little open part of this. Matches up perfectly with its partner there. Is G continuous at x equals -3? Yes. Now, you might be tempted to say, because the dot end fits right into the whole end of this, and yay. But we need to justify it. Our justification needs to be tight in terms of mathematical precision. We use the definition of continuity to explain your answer. The definition of continuity is that the two limits agree and that the point is actually there. So here's the most concise way to say that. Because the limit as x approaches -3 from the negative side of g of x is equal to the limit as x approaches -3 from the positive side. But that's not quite enough. The two limits have to be the same, and it have to actually equal g of -3. So they have to agree, but the point has to actually be there. Like this. Like these two here, they agree on what they're headed toward, but then when you get there, the point's not in the right place. So this is not continuous there. Whereas here, like these two things are headed for the same place, and when you get there, the point is there. So this is a nice, concise way to say that, because the limit on one side equals the limit from the other side, and that's equal to g of -3. And then you could say, like, which is 4, but that's not necessary. These three things have to be equal to each other, whatever they are. And that's the end of the Chapter 2 topic problems.